So we have seen connectivity is one, or connectedness is a topological property. A much deeper one actually, and a very interesting one is compactness. This is one thing where you get something for nothing in set topology. So this is roughly analogous to, so you can roughly think that compact space and continuous function is analogous to finite set and functions. So if you're looking at functions on finite sets, they are quite nice in many ways. They are very simple to deal with. If you have a continuous function on a compact space, this has similar nice properties. So for example, we'll see that if we have a continuous, so example is that we will see this next time, that if f from k is compact, to R is continuous, K compact, then F is bounded. In fact, it's bounded and it also attains its extrema. Since we are going to state this precisely later, I'm not bothering to write out the full statement. But you see, on an infinite set, a function need not be bounded, but on a finite set it is. And there'll be some point where it's at its largest and some other where it is at its smallest. So this is an example of these. So the formal definition you can think of as somewhat analogous to this, that if you have a finite set, then if it's a union of some subsets of this finite set, then it's a union of a finite sub-collection of these. If it's a union, so if I have a finite set, compact space, let's say X, and then if I have a finite set, call it S or something, if S is a union of certain sets, or even if it's contained in the union, if it lies in a bigger set, it's contained in a union, then it's contained in a union of finite sub-collection of the original collection. Okay. For compactness, we have to do this with open sets. Why? In part, like most of these definitions, it's over time you find the correct definition that captures the notion you want. And so here is the formal definition: a topological space. Space, let's say X, is compact if every open cover I should say, let script U be the whole cover, U which is some U alpha, alpha in A, has a finite subcover. So the finite subcover will be some U alpha 1, U alpha n. Just to clarify, that is, X is actually U alpha 1 union U alpha n. So if X is the union of all the U alphas, it's a union of only finitely many of them. So this is a kind of finiteness property. In fact, in metric spaces, it will turn out compact is actually finite at every scale in a precise sense. So this particular finiteness property, open cover has a finite subcover, is taken as a definition. So equivalent definition is if we take the complements of these sets, okay, and then take the contrapositive of this statement. Okay, so let's do this equivalently. Suppose F alpha, alpha in A, they are secretly X minus U alpha, is a collection of closed subsets. Subsets of X. Then I'll write the conclusion in a direct form, but often it's also used in its contrapositive. So suppose F alpha is a collection of closed subsets such that intersection of F alpha, alpha in A, is empty. This is saying union of the complements is all of X, that is, the complements are an open cover. Then F alpha 1 intersection F alpha n is empty for some finite number alpha 1 and alpha n. So as I said, we often use the contrapositive. We say that X is compact if given a collection of closed subsets such that all finite collections are non-empty, the full intersection is non-empty. This is a very useful way of saying it, because sometimes you want to produce points in the full intersection. It's like the Cauchy intersection property among real numbers. Okay, so this is the definition. So now let's look at our first theorems, which will illustrate this. Any closed subset, let me call it f in X of a compact space, is compact. This one is almost by definition, but it's a very useful way to construct compact sets. So once we know a space is compact, we'll eventually see that closed intervals, for example, are compact. Then we get lots of, or even closed cubes, then we get a lot of subsets, closed subsets of these, which are also compact spaces, so for which we can apply the conclusions of compactness. Okay, so a closed subset of this is compact. Okay, so let's take an open cover. U alpha, again I've written script U, so let U alpha, alpha in A, be an open cover of F. Of course we mean in the topology, which is the subspace topology, that is U alpha is F intersection V alpha, where V alpha are open in the whole space X itself. Well, this gives us an open cover, right? So the complement of F is open. Okay. Then, so if I look at V alpha, alpha in A, union the single set X minus F is an open cover for X, hence has a finite subcover. So the finite subcover is going to be V alpha 1, V alpha n, and possibly X minus F. But it doesn't actually matter whether the finite cover included X minus F or not. You can assume it does. Okay, so then U alpha 1, U alpha n is a finite cover of M. Of the set, we call it F closed set. Okay, so this is a useful criterion, as I said, but it illustrates just that many properties just pass to subspaces. Oh, incidentally, because of this being defined in terms of open sets, compactness is clearly a homeomorphism invariant. Though again, like connectedness, we'll see a stronger statement. Okay, but first we'll see a property which nicely illustrates how we use compactness in practice and gives a quite non-trivial result. So the theorem we see is that a compact subset of a Hausdorff space, let me call it K of a Hausdorff space X, is closed. Here compact means compact in the topology that comes as a subspace from X. So if it's compact in the topology that comes as a subspace, compact subset of a Hausdorff space is closed. This will illustrate very nicely how we use compactness, and indeed we will see that so we have to show the complement is open, and we will see the same proof gives you more. It will give you regular, it will give you normal, okay, from just the same hypothesis. So in fact, in Hausdorff spaces, which include metric spaces, so compact set is, so being compact is a property of the subspace alone. Being closed is a relative property. So Hausdorff used the term absolutely closed often for compact, because to him all topological spaces were Hausdorff. So being compact is the same as being closed wherever you're embedded, so long as your target is housed off, okay, which you assume as being non-pathological. So let's see the proof of this. So here we have K. What we'll do is we'll construct open sets. So given X in X minus K, we construct open Ux in again X minus K. Okay, then X minus K is, as we have done many times, union of X in these things of Ux. This is open. Okay, so for each point we'll find an open set, and this was a criterion for being an open set, in fact, and more explicitly it's the union of these. So the main thing is to find these. Now you're housed off, so given any point in X, so given let me say a point P in K, as X is housed off, we can find neighborhoods that separate these. Okay, so there exists, let's call this some neighborhood. So there exist, well, let me call them Vx and Wx. So this depends on both P and X. So let's call them Vp comma X and Wp comma X open, such that the point P is in Vpx and X is in Wpx, and Vpx intersection Wpx is empty. So for any pair of points I can find open sets like this. Now I want to fix only X, and I want to find a Ux and Vx which are disjoint. Okay, in fact that Vx is going to give us regularity free. So what we note that, so observe, as we vary P, the sets Vpx, P in K, this are an open cover for K. Actually, let me be precise and say take its intersection with K. So they're an open cover in a sense, but they're not contained in K. So since we were working with the subspace topology, these are an open cover for K. So there is a finite subcover. So we needed to separate only finitely many points. So Vp1x, Vpnx. Okay, so that is nice. We have only finitely many sets, and corresponding to that we have finitely many sets here. But finitely many neighborhoods, we can take the intersection, right? So we'll take a neighborhood, let U, P, not UP, it's just U, be the union of, let me just write it out this way. So we have this finite cover. So since these were called V, let's call it V. Let V equals V P1 X union Vp and X. I'm dropping the dependence on X because X is fixed. We are going to find an open neighborhood here. And let's call it W is, so now Ux, that was the one which was going to be called Ux. B, the intersection of the corresponding sets. WP1X intersection WPNX. Now you can have cross intersections. That is, all we know is that for one PI, the corresponding PI is WP. One PI, VPI and WPI are disjoint. Different points could have an intersection, but because we could pass to finite, we could take the finite intersection here, and something in the intersection has to be in all of them. So it can't be in any of these. Okay, so the disjointness will tell you that these two are disjoint. Then V intersection Ux are disjoint. Okay, and Ux is open. And Ux is contained in fact, X minus K, as K is contained in V. It's contained in these sets V. So we have shown that we have given any point, there's an open set contained here. So the complement of X is the union of these is closed. So remark, we have shown regularity. Namely, given a space, we have shown, well, it's Hausdorff, so it's T1, so we just have to show third separation axiom, namely, given a point and a closed set, there is an open set containing these, which is disjoint from all of these. There is an open set containing these and an open set containing K, which is exactly our set V here, so that they are disjoint from each other. So we have shown it's a regular and a similar proof. I'm going to call it an exercise, but I will draw a picture, a similar proof shows that X is normal. Okay. The idea being, given two sets K1 and K2, which are disjoint, closed subsets, so of a compact space. Compact subset of Hausdorff space is closed. We have shown that X is, we have not shown that X is regular. We have only shown that the compact set K can be separated. Okay, so similar proofs. Let me correct myself here. We have not shown this. Okay, so let's get rid of all this and say, and with just pictures, we'll see that X is going to be regular and it's in fact going to be normal. Similarly, X compact Hausdorff imply X regular, X normal. I've written it in two steps because we show regularity first and then normality. Namely, if X is compact and Hausdorff and we have a closed subset F, we use the same proof. Namely, if I have a point not in it and a point in it, Hausdorff tells me I can find an open set here and an open set here. So these are disjoint. This will give me an open cover of F, because it's a closed subset of a compact set. It's compact, so this open cover has a finite subcover, and I take the corresponding intersection to get disjoint sets. And now once you have, so we have an open set here, so this is exactly the construction that gave us our V and Ux. And now once we have regularity, we can upgrade to normality, because given two sets now, F1 and F2, okay, what we do is for each point, we can find an open set. Because it's regular, we can find an open set and an open set containing F1, so that these two are disjoint. Now in F2, we find a finite subcover and intersect all of these. So it's really the same idea. Okay. So now we are going to next turn to Rm. Before that, one more sort of general result which we need. And the general result we need is the following theorem. The image f of x of a compact set under a continuous function is compact. Again, if you think of it as some sort of finiteness, image of a finite set under a continuous function f mapping x to y. Of course, y itself may have many other points. This is like connectedness. And by the way, this proves homeomorphism invariance. We could see it directly, because if f was a bijection, then its inverse would also, and with its inverse continuous, then y would be the image, which would be compact, if x is compact, and vice versa. Okay, so you get a homeomorphism invariance of compactness. Image of a compact set and the continuous map is continuous. So namely, this is quite easy actually. Let U alpha in A be an open cover of f of x with the subspace topology, or we can think of it as intersection of f of x with open sets in y. whichever way we get almost the same proof. Then inverse image of open sets is open. So F inverse of U alpha, alpha in A, this is an open cover of X, hence has a finite subcover. And let me just say take image. So there are finitely many sets that cover X. The image of this finite subcover is actually going to be the finite subcover of, is going to give you a finite subcover of f of x. Okay, so these were general properties, and the last ones, the Hausdorff implying normal, but even before that, that in a Hausdorff space compact set is closed, illustrated how we can often use compactness. That is, point-wise things can be spread across, because there are huge number of points, but we need only finitely many. So anything stable under finite operations is preserved under compactness.